Okay, now let's look at the simulation of the Milton machine. The screen that you're seeing, we pull in a Milton machine. Milton machine is a combination of milling and turning, can be done in one. Depending on the machine type, it can let you do a 3+2 or a full 5-axis simultaneous. It depends on the control. If you have full 5-axis servos and controls, you can do a full contouring. At a bare minimum, most of the common controls in the market on a Milton will let you do 4+1. That means you can do X, Y, and Z, and the C axis on the main spindle will let you do full contouring, and the B axis will tilt. Let's look at right now the screen. The screen you're seeing, let's try to simulate a milling toolpath. We'll do the complete modeling in a Siemens NX. Then we apply the toolpath for the features. Then we will simulate those toolpaths. We'll go back and look at the actual how the actual part is done on the machine. This Milton machine will let you do any type of milling and turning features that you can think of at any given angle, any different compound angle, or any different trajectories can be done. Like I told you, either it can be done 4+1 or a full 5-axis simultaneous. Let's simulate the toolpath. Now I'm selecting a speed, animation speed at 100. Let's do it at the toolpath you're seeing here is of helical milling. Again, if you look at the videos, we are using a Siemens NX to model this part, and use a toolpath, apply the Siemens NX to create the toolpath. Now we are seeing the simulation. Make sure there's no gouge. The toolpath does what it's supposed to be. It's a good thing to go and simulate the toolpaths before you go do it in the actual machine. Thereby you can able to save a lot of cycle time. I mean a lot of time in proving out a process. Let's try to do it one more time so you can see it. So I will reset the simulation right now. In the next video, we will use the subspindle to come and grab the part, sync the main spindle with the subspindle. We do turning and milling in between both the spindle synchronized. Then we'll bring in a cutoff tool, do the cutoff, and then we can do all the back operation on the subspindle. So now we'll go and see the actual how the actual part is getting machined. Let's look at how to create a toolpath for a Milton machine. The part on the screen, you can see that it is round. Most of the features are round, but you cannot turn it because you can see a peg protruding, extending from the face of the part. So if you use the turning toolpath, if you try to do a facing, you're gonna wipe off the peg, the island or the tab that's sticking out, however you call it. So we may end up cleaning it out. So it's good to do a milling up on this. You can see the milling toolpath. Let's go and see what's there done in the milling. So for the milling, you can select a polar, you use a polar codes that are given in the Milton machines. You can do that. So select that and select a zigzag. You can select any one of them, but let's follow the contour with a zigzag. then clean the face on the top. Now we can do the helical milling. Again, for the machine method, you have to be really careful in selecting the tool and the method that you're trying to use to create the toolpath, because these are the features that these are critical, that are how you want to post out the code, the CNC code that will be called out while before posting into the control will be dependent on what type of milling method, machining method that you select. It's helical. Let's keep the ramp angle as 3. Look at the cutting parameters. It's a climb cut. Obviously, we don't to get a better finish. Keep the robust machining methods, machining practices. As long as your clamping is robust, strong enough, you can use a climb cut to withstand all the forces to get a clean cut, increase the tool life. Now you can do the helical milling for the bigger board. Do the chamfer. Surface area, select that cylinder to create the surface area, surface percentage. How do you want to contain your toolpath? The containment is critical by selecting the percentages. Again, helical, number of step overs. Again, the milling method is critical to get the code you want in the posting while posting. Now in the bottom dependencies, you can see what's the children, what's the parent, what is the tool that's used, what's the parent is the relationship between the child, and the turning workpiece is the parent, and then the turn main spindle. So the direction of cut, forward cut, the cut depth, variable average. Again, it depends on doing the first passes. For first few passes, you can have the max depth of cut. I'd set it at 10 thousandths max. Single pass it. Make sure how you want it. In this case, we are using a triangle insert. Triangle will be better for a good lead angle. You have good chip clearance and stuff. You can see how it generates the toolpath. Just making the chamfer. Now on the screen, the sketch you're seeing is a 2D sketch that will explain to you what are the turning operations that need to be done. As you can see, we can do a face cut, we can do a chamfer, then there's a groove. You need to come up with a grooving tool. So basically you can drill it or end mill it to create a clearance hole. Select a boring bar with a boring bar having enough clearance to go in and do all the ID work. Glue tool and come and do the chamfer, then do this taper. Now let's start selecting go into manufacturing. Now we'll start selecting the tool paths. Okay. Now what I did is I created a kind of a sample tool path for you to see. Say now if you want to create using a end mill to create the clearance hole, instead of using a boring bar, or instead of using a drill bit, you can use a end mill to go and create a helical path to create the clearance. Okay. In all the previous videos, I put in a step-by-step on how to select the toolpath, how to apply the turning and milling features for a mill-turn machine. Now you want to select its mill planner, you can select all the milling tools, and you got to select the turning. You can select all the, as you can see it in the legend here, it will tell you, explain to you. This is a left-hand tooling. What is turning? It's a 80-degree diamond. It's a right-hand tooling, 80-degree diamond to do the. If you want to use it as it is, as shown on the legend, the symbol, you can do this to select this layout for a subspindle, main spindle, subspindle, or you can the way how you turn. If you turn from the start of the workpiece into the chuck towards the main spindle, you can select and you want to select the spindle to go into the holder, then you select the left hand. The way how you spin the chuck, how the tool path starts from point A to point B, all this to come into effect in what type of tool direction that you create. Again, it's a 55 diamond. Now for the ID board, so the threading tool and the grooving tool, ID grooving tool, ID groove. Now let's select one of the ID groove. Come back in. So make sure that when you go back and select view, analyze the distance, understand what's the groove width, how deep the groove is, to select the grooving tool so that you have a nice chip clearance, so that you can go and pick it to create the roughing, and then go back and sweep it to create the nice clean tool path. Okay, so now that tells you the distance. Okay guys, now let's put a stock. Let's see how the stock will be for this part to turn. As I told you, it's an example part for a mill-turn machine. We'll do all the front operations on the main spindle, all this one all in the main spindle, and all this one in the back spindle. Let's again, it's an example part. Depending on custom operations, we'll go and depend on the user preference going forward. Type of part they want to see it turn, we'll do it. Now let's if you want to create the tool stock around it. Turn on the continuous stuff here. Okay, so now, since depending on how you do it, if you're metric, it's only all you need is only 40,000 1 millimeter of stock on the top to clean up, and on the face the same thing. Okay. So now this was the chunk that we'll be cutting in. Again, if you're gonna do that as a bar work, like a 12-foot bar in a bar feeder, the bar will be longer. So the remnant will be depending on how many parts that you're gonna make out of a 12-foot bar. Okay. Now to keep it simple, let's do this. Compare this. Select this one as a stock. Now you wanna go and spin it to select complete 3D modeling. This as a center line, you will be revolving the top layout sketch to get a 3D model. If you can see it in my previous videos, they will clearly explain you how to step-by-step modeling, part modeling, toolpath selection, selecting the tools, applying the toolpath, the mill turn. So we just seen it. This one is kind of an outline for example of a mill turn. What's done on the main spindle, what's on the sub spindle, how to select the tooling. Now let's select how it's turned on an actual machine, how to do a mill turn part. Chucking, again for a mill turn you can do a lot of work, right? You can do a long bar feeder, 12-foot bar feeder. It's a round bar or a hexagon or a different odd shape, different shapes. Again, for chuck work, either if it's net shape casting, forging, net shape forging, gross forging, or a simple bar work, create the chuck, slugs, depending on, then you can do that. Let's see how one of the example part is machined on a mill turn machine. And in the next video we will do that exact part that's been machined on a Milton. We will take it. If you like it, I will do it step by step, part programming, part modeling, part programming, and simulate it in the Vericut, and then we'll go back and do the complete steps to make the part. Let's see how it's machined. So if you had to simulate it and both the main and sub spindle, let's select the main spindle operation. So you can see this is the milling method that we selected is a polar mode. Based on that, you will get the output on the CNC codes. So right now we put a op stop. So I'm selecting for M01. I put a stop in there, so you can see. So the next one video we will cover the entire way of how to program each feature, how to do the part modeling, how to apply the toolpath, and then we do the simulation and look at how it's getting machined on an actual machine. If you had to do any particular type of product, please comment on the video. We'll do that. Thank you.